Okay, let's unpack this. For a while now, we've been using this sort of fragmented patchwork of tests to measure how AI sees the world.
Right, how it interacts with physical space.
Exactly. So our deep dive today is into something called SpatialTree. It's a new framework from researchers at ByteDance Seed and Zhejiang University.
And it really fundamentally changes how we measure what they call spatial intelligence, or SI.
Specifically for MLLMs, that's the AIs that handle both images and text.
And the goal here is, well, it's pretty critical. It's to move past all those simple, isolated benchmarks.
Towards something more unified.
A rigorous hierarchy, yeah. And it's inspired by human cognitive science. Specifically, Piaget's ideas about how we as kids learn to understand space.
So it's structured.
A clean four-level hierarchy. It progresses from just basic sensing all the way up to planning and acting in the world.
Let's walk through those levels then, L1 to L4, because they really build on each other. So L1, that's the foundation.
That's the bedrock, yeah. Pure perception. This is the raw, almost instinctive stuff.
Like,
It covers basic geometry, so the model just recognizing size, distance, shape, and also orientation.
orientation. I mean, like sensing gravity.
Exactly. Or just knowing if an object is upside down, purely from the raw physical input. No language yet.
Okay, so L1 is basically just physics. Then we move up to L2, mental mapping. This is where language starts to come in.
This is the bridge. It's where the AI starts to link that raw geometry to actual meaning.
Contextualizing it.
Yes, translating perception into semantics. So under L2, you get understanding things like spatial captioning, and this is key, affordance.
Affordance, that's not just knowing what a wrench is.
It's knowing that a wrench can be used for tightening a bolt, what an object affords you. L2 also includes building a memory, like a cognitive map of an area.
Got it. And L3 is where the heavy lifting starts, mental simulation.
This is the internal planning phase. This is all happening inside the model.
So things like,
Causal reasoning, predicting where a ball will go, or solving a geometry puzzle. And also sequential planning, figuring out a step-by-step strategy.
and all that leads to the payoff, which is L4, agentic competence.
This is the culmination. The MLLM has to translate that internal plan into actual physical action.
And they test this in real-world scenarios.
Oh, yeah. It demands goal execution. We're talking about manipulating objects with robotic grippers or navigating through a 3D simulation.
Okay, so once they mapped all that out, the really interesting analysis began.
Right. They confirmed what you might expect, that the high-level skills, L3 and L4, are really interdependent. But the most counterintuitive finding was actually down in L1.
The foundation, what did they find?
Well, the L1 skills, geometry, motion, they're largely independent of each other.
Yeah.
But here's the weird part. When they fine-tune the model on just one L1 skill, let's say distance perception,
Okay.
it could actually cause what they call negative transfer. It might make the model slightly worse at another L1 skill, like motion perception.
So improving one thing hurts another.
Just a little bit. It's like you're training one specific muscle so intensely that the fine coordination in a nearby muscle suffers. But, and this is the big but, that tiny setback came with this huge payoff.
A cross-level transfer.
A powerful cross-level transfer all the way to the top.
This is the mic drop moment, isn't it?
It really is. They saw that just by improving that basic L1 distance awareness, it dramatically boosted performance on complex L4 tasks.
How much of a boost are we talking about?
In one experiment, enhancing distance ability led to a plus 27.1% gain in robotic arm manipulation.
Wow.
It proves that foundational perception isn't just nice to have, it is a non-negotiable prerequisite for high-level action.
And that gets to this really crucial tension they found, right? The trade-off between thinking and perceiving.
Exactly. The team tried encouraging the models to think more, to use that verbose chain of thought reasoning.
But all that deliberation, that overthinking, it was actually bad for the fast, intuitive L1 tasks.
It was. The AI was too busy, calculating its next 10 moves to give an accurate, immediate answer on something simple, like a numerical estimation. Its precision went down.
They were confusing the two systems.
Like confusing System 1 and System 2 thinking in humans. The intuitive fast system of L1 versus the deliberate slow system of L3 and L4.
So what was the solution?
They called it the auto-think strategy. They built a reward system that's aware of the hierarchy. It basically tells the AI, look, if it's a simple perception task, stop thinking so hard. Just perceive. If it's a complex plan.
Then you can fire up the big reasoning engine.
Right. It balances that intuitive speed with deep analysis.
So this research, it really shows that scaling AI isn't about treating all tasks equally. It's hierarchical.
It is, and we have to respect that cognitive difference between the speed of perception and the deliberation of reasoning.
So What does this all mean for you? If a truly embodied AI agent needs to sometimes suppress its own internal thought to achieve that instinctive, accurate perception, what happens when that same agent needs to seamlessly switch between deep deliberation and instantaneous reaction without being told which mode to use?
That's seamless toggling.
That might just be the next great frontier.